For decades, our best theory of physics, the one that's supposed to explain everything, has been hiding this huge secret. It doesn't actually know why the universe works the way it does. We're going to dive into a new paper that suggests the answer isn't about particles or forces, but something much more fundamental: pure geometry.
I mean, it's really the biggest question you can ask, right? Why these laws? Why this specific set of rules for our universe? You'd think there'd be some kind of deeper reason, some fundamental principle that explains where the rulebook itself comes from.
And the answer? Well, it might just shock you. Our most successful theory of physics, the Standard Model, the one that's been tested again and again, it doesn't actually know. It just takes the laws of physics as a given, as a starting point.
So, let's talk about the Standard Model of particle physics. I mean, you could argue it's the most successful scientific theory in human history. Its predictions are ridiculously accurate, but it's got a secret, a deep foundational crack that physicists have been trying to paper over for years. Okay, so this slide really gets to the core of the problem. The Standard Model is built on what we call axioms, basically things you just have to accept as true from the get-go. It assumes the fundamental forces just exist, it assumes particles have the exact charges they do, and it assumes this very specific mathematical structure, that SU3 times SU2 times U1 thing you see, that's just the fancy math speak for how the forces are all glued together. Think of it like this: it's a perfect instruction manual for how to build our universe, but it says absolutely nothing about why these are the right instructions.
But what if we've been looking at it all wrong? A recent paper from physicist Paul Diamond throws out this wild idea. What if the laws of nature, the forces, the particles, all the rules aren't fundamental? What if they just emerge from something way, way simpler?
And that brings us to the heart of his paper. The idea that all of physics, everything we see and measure, might just be the result of pure geometry. It's a powerful concept called emergence, where you get all this incredible complexity and structure from a few incredibly simple underlying rules.
Now, to get this, we just need one key piece of the puzzle: the scalar field. It sounds super technical, I know, but trust me, it's actually pretty simple. Just picture a temperature map of the room you're in. At every single point in that room, there's a number, right? The temperature. That's a scalar field. And this theory says that at the bottom of it all, the universe is just filled with simple fields like that.
So check this out. It's basically a three-step process. First, you start with these simple scalar fields all over space-time. Second, the way those fields change and vary from place to place, their patterns, creates this incredibly complex geometric texture. You can imagine it like ripples and swirls on the surface of a pond. And third, and this is the totally mind-blowing part, the properties of that geometric texture are what give rise to everything we experience as reality. All the forces, all the particles, they're not fundamental things. They're just features of the geometry. And this quote from Diamond's paper, man, it just nails it. The fundamental forces that run the universe, what he calls gauge interactions, they don't just exist. They arise from the geometry. The physics isn't separate from the geometry. The geometry is the physics. Look, a beautiful idea is great and all, but in physics, that's not enough. A theory has to do work. It has to solve problems. And this is where this geometric idea gets really powerful, because it seems to naturally solve some of the biggest, most frustrating puzzles in physics today. To really appreciate what's going on, you have to compare the two ways of thinking. With the Standard Model, whenever we find a problem, the solution is usually to kind of bolt on a new piece, a new patch, just to fix that one specific issue. But this geometric approach, it's totally different. It offers one single, elegant idea that explains a whole bunch of different problems all at once. It's like the difference between just patching a leaky tire over and over again versus getting a brand new, better designed tire from the ground up. And we're talking about the big ones, the all-stars of unsolved physics problems. For instance, the theory suggests that dark matter isn't some exotic new particle we have to go find. No, it's just a really stable, tangled-up knot in that geometric texture of space-time. And that same basic idea also explains why protons live for so long without decaying, and it cleans up other deep theoretical messes, like the strong CP problem. It's not one fix per problem. It's one idea, many solutions.
Okay, but this is where it gets really exciting for me. This isn't just some neat idea that ties things up in a pretty mathematical bow. The absolute best part of any great scientific theory is that it doesn't just explain the past. It makes predictions about the future. It tells you what to go look for.
And that is exactly what this does. It makes sharp, specific predictions about what our telescopes should see when they look out into the universe. Predictions that can be proven wrong. This is what separates a cool idea from real science. It's not just sitting on a blackboard, it's making bets about the real world.
Here's a perfect example. The theory makes a very specific prediction for a number called the tensor-to-scalar ratio, which we just call R. So, what is R? Basically, you can think of it as an echo from the Big Bang, a measure of how powerful the gravitational waves were in the first instant of the universe. This theory doesn't just say R is, kind of small. It says, no, go look for this exact number, about 0.028.
And this is what gives me goosebumps. Look at that table. For R, the theory predicts 0.028. Our current best experiments have only been able to tell us that it's less than 0.036. I mean, we are right on the edge of being able to prove or disprove this. Future experiments are going to zoom in on that number, and if they find it sitting right where this theory says it should be, that would be absolutely monumental. So, where does that leave us? What does all this add up to? Well, we could be looking at the very beginning of a completely new foundation for physics, a true paradigm shift in how we understand the cosmos. And what's maybe the most incredible part of the story? This entire thing, this whole framework, from the deep geometric idea to solving dark matter to making these precise predictions, it wasn't developed by some giant lab or a huge collaboration. It was all the work of a single independent researcher, Paul Diamond. It's just an amazing testament to the power of one person with one really compelling idea. Now, let's be real for a second. This isn't a theory of everything, just yet. And Dimmitt himself is the first to say so. There are still big challenges to figure out, like fully explaining why particles come in different flavors or generations, and nailing down some really tricky mathematical consistency checks. He's presenting this as a starting point, a powerful new direction, not a final answer. And so it leaves us with this one, absolutely mind-bending question to chew on. Is it possible that our physical reality, this whole complex universe of forces and particles and light and life, is just a shadow, an emergent illusion cast by a deeper, simpler, and purely geometric truth? This paper makes a compelling case that the answer is yes, and hopefully our telescopes will give us the final verdict very soon. Thanks for listening.